Hello viewers, this is the third part of my lecture on catalysis. The outline of today's lecture goes like this. I'll recapitulate what has been studied in the earlier two parts, then I'll discuss about enzyme catalysis, what are enzymes, mechanism of enzyme action. The model suggested lock and key model and then induced fit model to explain the enzyme action. Then I'll discuss about factors affecting enzyme activity. Finally, I'll talk about some important applications of catalysis. To recapitulate what has been studied in the earlier two parts, I first explained the importance of catalysis in industry. I defined what is a catalyst and what is meant by catalysis. Now, there are several characteristics of catalyzed reactions which are common too. So, I discussed about it and how a catalyst functions. A catalyst functions by providing an alternative path of lower activation energy. There is lot of stress on activation energy and catalysts are able to bring down the activation energy so that the rate of reaction increases several fold. Now, then we looked at the classification, homogeneous and heterogeneous catalysts with some examples there, and we also looked at the theories of catalysis. Theories of catalysis, which is intermediate compound theory and then adsorption theory. Now, it's time for us to start with enzyme catalysis. What are enzymes? See, I am inhaling air and exhaling it. I want oxygen and I throw out carbon dioxide. So rapidly I am doing it. How am I able to do this? We can try to answer this question towards the end of our discussion on enzyme catalysis. Enzymes are nature's catalysts. Whatever discussions that we made on catalysts pales into insignificance when we look at the performance of the nature's catalysts, that is enzymes. They catalyze reactions in living systems. Without enzymes, the biochemical reactions will be too slow to support life. That speaks a lot. At one time, it was thought that enzymes exist in microorganismal level. Because they are found in living systems, it was thought that they are similar to microorganisms. But then a scientist called Sumner in 1920s was able to extract and crystallize an enzyme called Jack-Bean urease, and he showed that they are nothing but proteins. Since then, hundreds of enzymes have been discovered. Not only discovered, they have been extracted, crystallized, and their structures have been established. Protein structures can be established very well with the help of modern instrumental techniques, and X-ray diffraction has been able to exactly give us how certain enzymes look like. The molecular weight of enzymes range from 10 raised to 4 to 10 raised to 6 daltons, and many enzymes contain metal ions. Remember, our catalysts also are mostly metal ions or metal oxides, metal complexes, etc. Nature has also chosen metal ions to catalyze many of the reactions, and enzymes containing metal ions are called metalloenzymes. We can try to look at how enzymes are classified. Enzymes are classified according to the reaction or the type of reaction which they catalyze. Take for example urease. Urease belongs to the class called hydrolases. You can look at that ase, ASE, ending in the name urease, and most of the enzymes are named like that. And what then decarboxylases do? I don't have to answer this question, you know. Enzymes have unmatched activity, and remarkable selectivity. Here, if you want to compare what man-made catalysts do and enzymes do, we lag behind by several orders of magnitude. No laboratory-made catalyst has ever gone very close in activity and selectivity to the nature's catalysts. We are trying to imitate nature now. How best we can go close to enzymes in activity and selectivity. One reason, enzymes function at ambient temperatures, and many of the processes that we have in industries require very high temperatures. Energy input is very high, and therefore economics is not favorable. If we are able to bring down the temperature to room temperature, there is nothing like that. So catalyst definition, if you look back, a catalyst is a substance which increases the rate of a reaction without being consumed in the reaction. We can look at catalyst from another point of view. A catalyst will be able to bring the same rate that is desired, but at a lower temperature. That itself is a bonus for us. We may not increase the rate of reaction, but if we bring down the temperature from say 800 degrees centigrade to 200 degrees centigrade, we have achieved a lot. And that's what we look for. Increase in rate of reaction or decrease in temperature where that rate can be achieved. Enzymes have both. They have unmatched activity and remarkable selectivity, but all at ambient temperatures. Let us take one example. Enzyme urease catalyzes the hydrolysis of urea. The simple reaction is here. Urea hydrolyzes to give carbon dioxide and ammonia. And if it is used for hydrolysis of any substituted ureas, it doesn't function. That is the specificity of this enzyme. Let us make a comparison between a laboratory catalyst and the enzyme urease. The activation energy for the reaction, the hydrolysis of urea catalyzed by hydrogen ions, is 104 kilojoules per mole, whereas that catalyzed by urease is only 29 kilojoules per mole. In terms of time, if you look at, and in terms of concentration, we look at what this amounts to. At equal molarities, urease is about 10 raised to 12 times more effective than the acid catalysts. Let us look at from the time point of view. Suppose if this reaction takes 1 month to attain equilibrium, by using a laboratory catalyst, that is mineral acid, the same reaction, if it is catalyzed by an enzyme, will reach the equilibrium in less than an hour. So that is the comparison. How an enzyme works. Despite their biological origin, enzymes have characteristics very similar to the man-made catalysts. They are no different when they function in a given reaction. Look at this. This is the familiar diagram that we had shown when we discussed about how a catalyst functions. Look at this. This is the activation energy that you have for an uncatalyzed reaction. The reaction profile, energy profile that you have is this for uncatalyzed reaction. For the catalyzed reaction, we have the dotted line. The energy of activation for a catalyzed reaction is much smaller than the energy of activation for an uncatalyzed reaction. That exactly applies to even enzyme catalysis. So they are no different from the laboratory made catalysts. Interestingly, the enzymes that are available in nature can be extracted from their source, purified, crystallized, and we can use them to catalyze reactions that are important in industries. The same way, they will give us similar activity and selectivity. But then there is one hitch here. We should be very particular about the conditions. Why? Because enzymes are proteins after all. And proteins we know are very sensitive to changes in temperature and the environment, especially the pH. If the pH drifts much away from the optimum pH, the enzymic activity is killed totally. Similarly, as the temperature increases beyond 50, then the enzyme activity dies down. This is because the denaturation of proteins. It loses its structure and thereby its activity. Mechanism of enzyme action. Simplest scheme to explain enzyme action is given by Michaelis-Menten mechanism. E plus S gives us ES, which then in turn gives us E plus P. What does this mean? E stands for enzyme, S stands for substrate, and ES stands for enzyme substrate complex, which then decomposes to give back the enzyme. It is free to take up another molecule and we get our product. This sounds familiar. This is exactly what we try to explain in intermediate compound theory. The catalyst reacts with one or more of the reactants to give an intermediate compound. In place of that compound, if we put enzyme substrate complex, everything falls in line, very similar. And kinetics of enzyme catalyzed reactions are mainly based on Michaelis-Menten mechanism. To explain how enzymes are so specific in their action, a model has been proposed which is called the lock and key model. You can clearly look at it. Enzyme, the site of binding in the enzyme and the shape of the incoming molecule match exactly. Like a key fits a lock, and with that key only the lock can be opened. And here is the best example. If you can fit in here as shown here, once it gets into the cavity, the reaction takes place. Enzyme will break down the molecule into the fragments. If it is the food, it breaks down into nutrients. Very interesting, isn't it? But then enzyme's structure in this particular case, like lock and key, was thought to be rigid. Not necessarily. Enzyme is made up of several amino acid units, and all of them are not involved in the catalytic action. Most of them support the transportation of the substrate to the active site. Only a few amino acid residues are involved in the actual catalytic process. But then there are enzymes which show relative specificity, not necessarily for one molecule, a group of related molecules. In order to explain that, where the shapes of the molecules are slightly different, we have to go for some flexibility to the enzyme structure that we can see in the induced fit model. It need not match exactly, but it should adapt slightly to the incoming molecule. That is the essence of induced fit model. Now, there are several factors affecting enzyme activity. We have seen factors affecting the catalytic action in our laboratory made catalyst. Similarly, there are factors which influence enzyme activity. Concentration of the substrate. We are keeping the concentration of the enzyme constant and then vary the substrate concentration. When the substrate concentration is low, activity is low, and as the substrate concentration is increased, the activity starts leveling off and finally reaches a maximum, at which we have maximum activity. Why this happens? Initially, many of the enzymes' active sites are vacant, and as you increase the substrate concentration, most of these active sites starts functioning, and then a stage comes because of limited availability of enzyme where we have kept its concentration constant. All the sites become saturated, they become functional. The substrate molecules beyond a particular concentration have to wait for their turn to get into the cavity and react. The other important factor that we have is the concentration of the enzyme itself. In studying this, we keep the substrate concentration constant, and let us look at how it varies. The activity of the enzyme, otherwise it is the rate of reaction in normal terminology, it will increase linearly with the increase in concentration of the enzyme, because you are making more and more active sites available for the substrate that is present, and as the enzyme concentration increases, the rate of reaction therefore increases. The third factor that influences the enzyme activity is the temperature, about which we have just made a mention earlier. How it affects? At lower temperatures and at higher temperatures, enzyme activity is almost nil. As the temperature increases, the enzyme activity increases, reaches an optimum activity, and the temperature is optimum temperature, and beyond which the denaturation of enzyme begins. Activity goes down drastically and falls off. Enzyme becomes totally inactive. Therefore, whenever we use enzyme, we have to have the temperature control within or in the vicinity of the optimum temperature. And the fourth factor that influences enzyme activity is the pH of the medium. Biological fluids have different pH, enzymes have to function, and if you look at how pH influences enzyme activity, again you have an optimum pH at which the activity of the enzyme is maximum. On either side, the activity drops down sharply. So, enzyme will function in the vicinity of the optimum pH, but in this particular case, you have optimum pH depending on where this enzyme resides. Different enzymes have different pH, optimum pH values. You can see here 2, 7, 10, and different enzymes have different pH values, the narrow range in which they are stable and they are functional. It is now time for us to look at some examples. First, look at an important example of homogeneous catalysis using soluble metal complexes. It is the Wilkinson catalyst for hydrogenation of olefins. The catalyst is rhodium triphenyl phosphine complex, a very successful catalyst because it is able to bring about this reaction under ambient conditions. And after the success of this catalyst, again there is interest in homogeneous catalysts. Why? Because their properties can be tailor made. We have many parameters to control so that we get desired activity in the metal complex. What are they? The metal and its oxidation state. You have a choice of metals and with varied oxidation states. You can choose a ligand, you can choose its polarity, chiral ligand if you want enantioselectivity. Metal to ligand ratio can vary in designing the complex, and since these catalysts are used in solution, you can choose the solvent, you can vary the polarity of the solvent. Industry has applications of catalysis in food industry. The best example that we have is the hydrogenation of oils. You remember dalda? It's margarine that you use these days. You have industry which manufactures fine chemicals. We have pharma, dyes, cosmetics, etc. Then we have petroleum industry where we carry out cracking reactions and reforming reactions in order to get desired products. Cracking means breaking down larger molecules into small molecules. Reforming means say cyclohexane to benzene. And then petrochemical industry, and you have a host of monomers that are used in synthesizing polymers like styrene, caprolactam. Caprolactam is the monomer for nylon 6. Now, this is a classic example of the success of heterogeneous catalysis. Manufacture of ammonia, which caused revolution as far as agriculture is concerned. The food problem of the world was almost solved because of this one simple reaction. And this reaction is exothermic. So we prefer low temperature and high pressure to carry out this reaction. The catalyst is iron based catalyst. We use magnetite for its synthesis, but then you have a large number of promoters that are added to this formulation: potassium oxide, alumina, calcium oxide, silica, magnesium oxide, and then some oxides in trace amounts: titanium, zirconium, vanadium. We want the activity to be maximum, and you can imagine this catalyst, in spite of all this, is susceptible to some catalyst poisons. We have to avoid them. And then if you look back, more than 100 years ago, this formulation was patented and it is still in use. That shows the success story of this particular catalyst and the process. The second example again involves ammonia, oxidation of ammonia in the manufacture of nitric acid. The steps involved in the reaction are these, and here we use the platinum sponge initially, that was patented in the year 1838. Then it was found that it is not that suitable. A platinum gauze was used, very fine mesh with apertures 1050 apertures per square centimeter. That was showing some recrystallization of platinum, formation of crystallites, decreasing the activity, making the platinum wire brittle. A platinum rhodium alloy is used with about 10% rhodium in it, and then this reaction is exothermic, and therefore once heated it can be self-sustaining. The contact time being very low, we are using a wire mesh, and that has to be supported on a ceramic support for the success. And most important of an example is the catalytic converter. It we come across in day-to-day life. Automobile pollution has been got over to a great extent by the use of the catalytic converter, because the automobile exhaust contains polluting gases like carbon monoxide, oxides of nitrogen, and unburnt hydrocarbon. How to get rid of it? Use a catalytic converter. What it does? It brings about three reactions. That's why it is called three-way catalyst. Platinum, palladium, rhodium on alumina as a wash coat supported on cordierite monolith is fitted in a small container which is fitted to the exhaust, through which the exhaust gases pass. And the two reactions that it carries out, two are oxidation reactions, where carbon monoxide is oxidized to carbon dioxide, hydrocarbons are oxidized to carbon dioxide and water, and oxides of nitrogen are then reduced to nitrogen. Thereby we eliminate all the pollutants that are present. Now I ask you a question. Have you got the PUC done to your vehicle? Now we come to the end of the lecture on catalysis. Let me summarize what we studied today. We studied catalysis from the starting point in earlier lectures and came to enzyme catalysis in this lecture, in which we discussed what are enzymes, mechanism of enzyme action, lock and key model to explain enzyme action, induced fit model to account for the flexibility of the structure of enzyme, and then factors affecting enzyme activity. Finally, we looked at applications of catalysis. That brings us to the end of our lectures on catalysis. Thank you very much.